Thank you for having me. So I'm going to be telling you about some joint work with Azet Koskun, Suchitra Pandey, and Kevin Tucker. And so the main result itself is pending one important phrase, actually pretty easy to state. So I'm just going to kind of put this up here right now. And so my goal here is, okay, the very important phrase is what actually is a limit F signature function. So we're going to first go on a little tour of some numerical invariants and positive characteristics that will let us actually, this slide will come back later on when we can actually understand it. And then maybe we'll talk a little bit about how you might compute something like this if you wanted to. So to start out, okay, there's a whole lot of words up here, but what I want you to be visualizing is you have your favorite finite field or maybe an algebraically closed field of characteristic P, and you're going to take something, polynomial ring over that, mod your favorite ideal, localize at your favorite prime. Like this is the kind of ring we're going to be working with. And so since we're in positive characteristic, we have this Frobenius map that is a really powerful tool. And so it's just going to send an element R to its pth power, and because we're in positive characteristic, this is actually a ring map. It turns out that the module structure we get on R via this map carries a lot of information about the singularities of R, but it's really confusing to have two different copies of R with, R kind of viewed normally and R with this different module structure. So it's common to use this, alternate notation of this F star R. So this is just a formal symbol that I'm sticking on all of my elements of my ring. And the point of it is to illustrate what this module action is. That said, in this talk, we're not going to be diving too much into that module structure. So if you prefer and your ring is reduced, I can actually think about the Frobenius as R embedding into its pth root ring, just via R goes to R, right? Thinking of this as, okay, well, R to the 1 over P to the P. Later on, we'll also be iterating the Frobenius a lot. So, P to the E is everywhere instead of just P's. And an ideal that's going to come back to us is this idea of a Frobenius power. And so unlike a normal power of an ideal, I'm just going to take the appropriate power of every element of the ideal and take the ideal generated by that. But a cool fact is I could also get away with only taking a generating set for I and taking these powers, and that will give me the same ideal and is not affected by your choice of generating set. So, okay, so the first thing we need to define is the F signature. And so this is going to be a certain limit as we iterate the Frobenius. And so what's going on here is I'm interested in breaking down this module into a bunch of free direct summands, so a bunch of copies of R, and then some remaining stuff. And so this AE is telling me, okay, well, what is this maximum number of free copies of R I can find inside of this module? And then this is going to probably grow very fast. And so we have this scaling factor in the denominator there. And then D is the dimension of my ring. And so you are probably looking at this and are like, well, this is a kind of random looking definition. Like, why this choice of AE? What's going on here? But it turns out this connects with kind of three interesting kinds of singularities. And so the first one is I can talk about a ring being F split. It literally means that the Frobenius splits as a module map. So rather practically speaking, right, if I have this splitting, this means that, well, I have a copy of R living inside F star R as a direct summand. So at the very least, A1 has to be at least 1. Okay, and I also said this was a kind of singularity. This is a pretty mild restriction on your singularities, but for example, if you're F split, you're at least a reduced ring. Okay, and then a much stronger class of singularities is, well, strong F regularity. And so this is a kind of similar format in my definition, but now I'm looking at, instead of just 1, I'm kind of considering other non-zero divisors. And I want to be able to find a map that will send this guy to 1, except it turns out I might need to consider going to a higher iterate of the Frobenius if it's not the element 1 specifically, but that's okay with us. And in some vague sense that we'll talk about on a later slide, this means that F star ER should have a lot of copies of R inside, right? I have like a lot of different of these, a lot of kind of these different projection maps here, and you should be expecting, okay, well, yeah, I should probably find, like not all of these direct sum ends should be the same one. Okay, and then finally, oh, and I guess in terms of singularities, right, so a strong F regularity, if you've not seen this before, it, for example, implies your ring is Cohen-Macaulay, it's normal, it's pseudo-rational, so like a much nicer ring than just saying reduced. Okay, and then finally, regular rings are very nice rings. And in our setting, we can state Kunz's theorem as this ring R is regular if and only if every single one of these F star ERs is legitimately a free module, which of course means it should have like the most free copies of R possible. And it turns out you can compute that this maximum number of copies possible is P to the ED. So that's where that denominator was coming from in our definition. That's why we chose it. This is like really the maximum number. So some properties of this. Okay, so I just kind of vaguely explained why this F signature should be between 0 and 1, but maybe some other useful things. Okay, it's a limit. The limit does actually exist. Like we are studying something interesting. I didn't need to throw some like lim sups or lim ints in there. And it turns out, right, so when I said strongly F regular means you have a lot of copies of R, it turns out the F signature is positive if and only if your ring is strongly F regular. And it also turns out that this invariant is 1 if and only if your ring is legitimately regular. And so Kunz's theorem is one direction of this. If you're regular, it's the limit of the sequence 1, 1, 1, 1, 1. But this is also telling you in an asymptotic sense, right? If you're even approaching 1, then actually you just had to be equal to 1 the whole time. And so maybe, oh, yes.
Are there interpretations for numbers that are strictly between 0 and 1?
So I think there are some maybe more specific results you can say that I don't trust myself to quote off of the top of my head. But the sense that I have at least is that the larger your F signature is, the nicer and like the less singular in some sense your ring is. And so that's what I would like all of you to be envisioning, right? So 0 is kind of the worst case. You're not even strongly F regular, and there's a lot of badness that's hiding in 0, but beyond that, okay, larger is better for us. Other questions? Okay, well, so I should give you some examples. And so maybe a nice simpler example is if I have a polynomial ring, the nth Veronese, the F signature is 1 over n. And so thinking of the interpretation I just said, okay, so the higher the Veronese the higher n you're taking a Veronese with, the kind of worse, the kind of more singular your ring is in some sense. Well, n equals 1 is kind of the best ring though, right?
On the right.
But okay. So at the very least, yeah, we'll say definitely n equals 1. This is a ring we understand. That's polynomial ring, so it should be 1. And then this is just, this one is just here as like a more interesting example, right? We can see, okay, 1 over n, that's like a pretty nice formula. This is not a very nice formula. Like notice this floor of p over 3 we've got going on here. So not great. I will point out, as a gets, as p gets larger, this a will get larger. So this denominator will get larger. And so we're going to get 1/8 minus something that's getting smaller and smaller. And so in some sense, this is saying for larger p's, oh yeah, sorry, yeah. So a is that guy down there. So this is kind of saying that for larger and larger p's, this is a nicer ring. And this is an idea we'll maybe come back to later. I should also say, I've given you 2 examples here, but the F signature in general is kind of hard to compute. So this is something else to keep in mind. So, okay, so now we're going to kind of generalize a little bit. And so maybe instead of thinking about R mod F, it might be nicer to think of a pair of R and F, especially if, say, your ring R is regular, because then you can hopefully utilize something about this R. So if you are already a positive characteristic person, one example might be you're thinking about Fetter's criterion, somehow it's maybe easier to think about this lift in the polynomial ring and compute stuff there rather than in the quotient ring. If you're not a positive characteristic person already, I'm sorry that was a completely unhelpful statement. So the point, though, is that I'm somehow going to be thinking of this R and this F, and I'm going to describe a function in terms of this real number t. And I am not going to formally describe what this is, but the point is it's a kind of similar limit to what we had before, the same denominator. This b sub ft and e is still counting some kind of free summands of this f star er, but I want these to be built out of f somehow. And so maybe the most I'm going to say is that they're going to kind of, these projection maps, I want them to like factor through an appropriate power of f. And an appropriate power here means something to do with t and with this p to the e as the e is growing here. And I'm not, it's best if we don't get into any more detail than that. So I will instead, though, give you some useful properties. And so this is kind of more what I want you to think about when you're thinking about the F signature function. Yeah, question.
Why do we want F?
This is a great question. The answer that I'm going to give off the top of my head, which may be slightly wrong, and I can talk to you more about it later, is that I think this is just, like, if I'm being motivated by thinking about R mod F, if I'm taking this in the maximal idea, like suddenly that's just not interesting. So, I guess also F should probably be non-zero, and I didn't say that, but it would also not be very interesting if F was 0. So I'm thinking of this as a make this be interesting condition rather than like a hard thing. But I'm not going to fully stand by that answer without thinking more about it. Okay, so some properties we have here is, okay, this F signature function psi, this is analytically speaking like a pretty nice function. It's Lipschitz continuous, convex, and it's non-increasing. And the original definition I gave you was vague, but if you're plugging in t's of this specific form, so a rational number with a power of p in the denominator, you have a very explicit description of what the F signature is. And this is nice for actually computing things, right? This is very concrete. Okay, and I've also given you some specific values, right? So some derivatives are carrying some information about the F signature and the Hilbert-Kunz multiplicity of the quotient ring. Hilbert-Kunz multiplicity is another numerical invariant, kind of like the Hilbert multiplicity, but somehow more positive characteristic. And this function will eventually be 0, and it becomes 0 when I pass the F pure threshold, which is another numerical invariant, like a positive characteristic thing. And this is thinking more about being F split. So like measuring like how far away this quotient ring R mod F is from being F split. Okay. So now, finally, I can actually tell you about the limit F signature. So, right, we already had one limit that was inside the F signature, but now we're taking another limit. And so this is, like, so thinking back to that example I gave of that 1/8 minus that super gross thing, somehow as the prime got large, that's approaching a really nice number of 1/8. And so there's this more general idea that if you have, some polynomial or something with coefficients in the integers, I can then think of that polynomial in FP, the polynomial ring over FP, just by taking all of those coefficients mod P. And there's this kind of vague sense, like, and there's like concrete examples of which you can have something in characteristic 0, take it mod P, and then maybe for large P, or maybe in some limiting sense, you can connect some positive characteristic statement to some characteristic 0 statement. So for example, there's some characteristic 0 kind of singularities called KLT. And if you take reduction mod P, this should be telling you, okay, well, my original guy was KLT, whatever that is, if and only if for, large primes, my reduction mod P is strongly F regular. Or in the limiting sense, there's a numerical invariant called the log canonical threshold. And if I go mod P and then take this kind of limit, of the F pure threshold, I actually get back the log canonical threshold. And so this is kind of what I mean by like we should have some kind of connection. And so we can define the same thing, right? This F signature function. Well, we can take a limit as p goes to infinity. And maybe, hopefully, this will tell us something about characteristic 0. But this is a somewhat newish definition, and there's actually a lot of open questions about this still. Like, does this limit always exist? Is this limiting function continuous? Is it, are there, could we say anything about when it's something nicer, like maybe a piecewise polynomial thing? And these would all be great questions that I would love for someone to answer. So please go try and prove some things about this, and I and other people will be very happy. And so this leads us back to our results. So the point is this limit F signature function. Okay, in general, right, I said this limit might not exist. Is the limit even continuous? What can we say here? So in this specific case, we can actually say something like very specific, right? This limit did exist. It converged to something continuous and even piecewise polynomial. Now that I didn't actually define LCT or FPT, but nonetheless, I will say something about them. We have these two cases here. And as it turns out, these two cases are exactly reflecting the fact that the log canonical threshold of that polynomial is either 2 over a plus b plus c or 1 over a. And it's kind of 1 over a exactly in this case 2, and it's 2 over a plus b plus c in exactly case 1. So like this cutoff point is the log canonical threshold. And well, that's good because that's kind of where the cutoff point was for the F pure threshold. The regular F signature functions became 0 at the F pure threshold point, and I told you the FPT limited to the LCT. So that's why you should expect there to have been cases like this if you say already knew that there were cases for the log canonical threshold here. And I do have time remaining, so I will also tell you, hey, if you wanted to compute some limit F signature functions, what are maybe some tools that we use that might also be useful to you? And the first one is unfortunately analysis. Okay, there's a lot of text on this slide, which I feel bad about, but kind of what you should be thinking is, okay, I have this capital psi, it's a candidate F signature function. I don't know whether it's my limit F signature function yet, but it kind of at least is continuous and it satisfies like the right endpoint and like non-increasing properties. Kind of the big takeaway is that, okay, well, if I can find some kind of nice specific sequences, I can get some kind of uniform convergence statements. More specifically, the takeaway here is in this last sentence, I can get away with only computing the F signature for T's of this specific form of K over P. Because of this like nice continuity and convergence I had. And that's useful because one of our properties of the F signature function was we actually have an explicit formula for rational numbers of this form. So this really means all we need to compute is this length of this ideal. So immediately this is far more concrete. Another useful tool is, okay, our specific function, we have that x to the a and the y to the b out front. And that's maybe a little bit, hard to work with, but it turns out that we can kind of pull out this x to the a and y to the b, and we'll have this other ideal, but we'll have this explicit connection between the lengths. So we can work with this ideal down here instead. Okay, we have this trade-off of the power of x and the power of y are no longer the same. But it turns out that's far easier to deal with than having the x to the a and the y to the b stuck onto our polynomial. So we were like glad to make this trade-off. And the final tool is only useful for kind of a polynomial like this, but it was very cute, so I wanted to tell you anyways. So right, x plus a to the c, we're expecting to get some binomial coefficients showing up a lot of places. And both of the two different ways we ended up proving what these lengths were somehow both intrinsically relied upon the fact that if you have a determinant of binomial coefficients of this specific form, and p is large, whoops, where is my pointer? Okay, if p is large enough relative to your other parameters, then this matrix is invertible in characteristic p. And I'm always a sucker for cute combinatorial determinant formulas. So, and so with that, thank you for listening.